walk hypothesis states that the past movement of a stock's price does not affect its future movement. The daily change in a stock's price can therefore be modeled with a random variable. The change in a random variable is not completely random, however, because it can be modeled with a probability distribution. One such distribution is the normal or Gaussian distribution, a picture of which is on screen, which is often used to model the random walk of stock prices. In this video, we will use Python to explore stock data and to analyze the normality of stocks. In other words, we will see whether real-world stock data does indeed follow a normal distribution. One note about this video: don't worry if you're not too familiar with some of the concepts discussed. Throughout the video, there are annotations that link to helpful videos which can give you background on all of the concepts used in this video. So you might have seen an annotation already which links to a video that discusses the normal distribution. One final note before we start talking about the actual code and stocks is that this video is broken down into 3 chapters. Part 1 is gathering your data, Part 2 is analyzing the data, and Part 3 is a brief exploration of the effect of outliers. So without further ado, let's gather some data. So in order to begin looking at stock data, first you need to gather the data. So the easiest source that I've found to find such data is Google Finance. So you can go on Google Finance and you can simply search for a stock up here, so you can type in any stock. I use General Electric, so I can just type in General Electric Company and it'll come up. The code is NYSE:GE. Then you can go to historical prices and it gives you daily prices for the last year. So once you get to this screen, you can see right here there's a little button that says download to spreadsheet. So if you right click or control click, just secondary click this button, then there's an option to copy link address. So that's what you want to do. You want to copy the link address. Then once you copy the link address, now you can access something called a CSV file of this data. So CSV file is a comma separated value file, which is a little bit like a spreadsheet or a table, and it's easy for a computer to read. So if you look at the annotation right now, there's a video that discusses what a CSV actually is and some basic ways to use a CSV file. So once you've copied the link to the CSV file, you can start writing code to actually look at the data. So I'm writing my Python code in something called a Jupyter Notebook, and understanding how to set up a Jupyter Notebook is really important. So before you continue, I would strongly urge you to watch the video that is linked in the annotation right now. Okay, so I'm assuming that now you have some familiarity with a Jupyter Notebook and you can follow along. So first, what you're going to do to look at the data is import something called pandas, which is a Python library that helps with looking at data and data manipulation. So I imported pandas as PD, so I just imported it as PD so that it's easier to refer to. I could have just imported pandas and then written pandas in a bunch of places, but instead, as you'll see later, I just have to write PD. So then what I did was I defined the variable URL as the link to the CSV. So I just got this from the previous step where I copied the link address. Then you can take advantage of a function that's built into pandas called readCSV. So if you write pd.readCSV and then the parameter is the URL, so I just use my variable URL there, then I could store that in something called a variable called stocks_data. Of course, you could call stocks_data whatever you want. So now I have all my CSV data stored in this variable stocks_data, which is right here. The random walk involves the change in the stock price every day. So to look at the change in the price, we have to take the price on one day and subtract that from the price on the next day. So then we get a change in price. And so I chose to just look at closing prices. So closing prices are the stock prices at the end of the day. And so I calculated the change in the closing price in this delta closing column, as you can see in the table below. So I can create a new column in the CSV called delta closing just with this syntax. I defined my new column, so stocks underscore data, then in brackets I put the name of the new column, and I defined it as data in the column named close minus the data in close dot shift. So dot shift would give the previous row. So that way I could, for example, have this value, the highlighted value of delta closing, equal to the closing price on day one, on index 1, minus the closing price on index 0. So then once I created that new column, I could just print out stocks underscore data, so the entire modified CSV in a Jupyter Notebook, so you can see there's this big table below. So it doesn't actually show all of the values because I think there are 251 rows. It just has these ellipses there, but at the bottom it says there are 251 rows and 7 columns, so I know that all the data is there. So now that I have this table, I have successfully gathered the data from my CSV, and I've also created a new column which will be very useful to me going forward. So now that we have our full data table from the CSV consisting of several different values, but notably the column that we created, delta closing, or the change in closing price, we can now think about how to see how normal our data is. So the way we'll do that is we will first graph our data and a normal probability density function, and then we will use a statistical test to compare the two and to see if they're statistically different or statistically the same. First, though, what we want to do is we want to create a new data table. In Pandas, it's called a data frame, but essentially you can think about it as a data table called change underscore closing, or that's what I called it, which is just the column of the change in closing price. So you can see this code right here signifies just the change in closing price. Then Pandas has a nice built-in function called .describe, which gives you several different statistical values. Now, we don't need these right now, but they will be useful later, and you'll see later in the video why they're useful. So then once we have change underscore closing, our new data frame, we can make a histogram of the change in closing prices. If you don't know what a histogram is, please watch the video in the annotation before continuing. It will be really important going forward. So now I'm assuming that you know what a histogram is. So you can see here that I've created a histogram. And the way I did that was with something called matplotlib. So matplotlib is a library in Python that lets you make graphs and plots and things like that. So to access matplotlib, import matplotlib.pyplot as PLT. Again, the as PLT part is just to make it easier to write out. I also imported numpy as NP. Numpy is a Python library that helps you do math, and that'll be useful a little bit later. This line of code right here, the %, then matplotlib inline, that's a way to get your figures to print in line. So right after this cell of code, you can see the figure printed. So I'd recommend writing that. But you can see the code here is quite simple. We just used matplotlib's hist function. So we could write plt.hist. Then remember, change underscore closing is the data frame that contains the change in closing price. Then we used these two lines of code just to label the X and Y axes as change in price and frequency respectively. And then there's this histogram. So you can see that it peaks around in this bin that starts maybe around negative 0.15 and goes right around to 0. And if you remember the original normal distribution picture from the beginning of the video, the bell curve shape, this kind of seems like it resembles a bell curve, but obviously not perfectly. I mean, there is a hint of symmetry in that both sides around the peak do have the same shape, but we can analyze how normal it is in a few minutes. So then what we want to do is we want to create a normal probability density function. So a bell curve based on our data. So a normal distribution is created based on just the mean and the standard deviation of the data set. So the mean is signified as mu, so the Greek letter mu, which is mu, and this is where numpy becomes useful. Numpy is a function called mean, so np.mean, and our data frame just gives the mean of the data frame. Variance simply is just standard deviation squared, but we can use numpy's VAR function to calculate variance, as you can see here. And then sigma stands for standard deviation. So sigma is just the square root of variance, as I said before. So we can use numpy's square root function on the variance variable to calculate the standard deviation. Then, this line of code signifies all of the values that we want represented in our final curve. So this numpy.linspace will create a set of values that are between, so np.amin is the minimum of our data frame, and np.amax is the maximum. So it's the minimum and the maximum, and then this final parameter is the number of values. So basically it takes 100 values between the minimum and the maximum of our data frame. Finally, we can use the plot function right here, so plt.plot, to plot our bell curve. And so you can see the first parameter is x, so the range of values that we created a second ago. Then this whole thing is actually just the formula for the normal distribution, which I will pull up in a second. This is the formula for the normal distribution. Mu is the mean. This sigma is the standard deviation. So we can just write that formula in Python right here, and that will allow us to create a bell curve that works for our data. So after doing this, we can compare our histogram. We can visually compare our histogram up here to the bell curve we created down here. So the bell curve is a normal distribution, and the histogram is the real world data. And so if we find that the histogram looks a lot like the normal distribution, then we maybe have a hint that the change in stock prices, or the random walk, does follow a normal distribution. So you can see here, the first thing you have to note is you have to use this line of code. So you have to define the data frame as the data frame, but with this function .drop NA. So what that does is it drops empty cells. If you don't do that, then you run into a few problems. The rest of the code you've seen before, and if you want to play around with this code, I will put it in the description. But the one key difference is this little this little parameter. And up here you can see that we didn't have it. So adding normed equals true normalizes our histogram and allows us to put both, allows us to keep both the histogram and the bell curve, or the normal distribution, at the same scale. So you can see here, this is our normalized histogram and our bell curve. The y-axis doesn't actually show the raw frequency anymore. You can see it's 80, 60, 40, but down here it's 1.75, 1.5, etc. Instead, it shows a relative frequency. And then the x-axis is still change in price. So you can see here that the bell curve and the histogram do seem similar. I mean, especially around these points and these points, the histogram does approximate the bell curve. Around the top, however, there is some difference between the two, but we can use something called the D'Agostino and Pearson's test, which combines two elements of a distribution, the skew and the kurtosis, to produce a test of normality. So it tests if the data is normal or not. So skew and kurtosis, watch the video in the annotation now to understand what they are. So in order to do this test, you have to first import scipy.stats. So scipy is another Python library, and I just imported it as stats so that it's easy to refer to again. So then we can use stats.normaltest. Normaltest is a function built in, and we have change_closing, or our data frame, as the parameter. So once we do that, we can run our code and it outputs this. Now this looks a little bit messy, but there's one key number to read here, which is the p-value. Now if you don't know what a p-value is, I would encourage you to watch the video, but in simple terms, we can think about a p-value as a way to see statistical significance. So generally the magic number for p-value is 0.05. So if a p-value is below 0.05, then two sets of data are statistically distinct. They're different. But if it's greater than 0.05, then they are not statistically significant. They're not statistically distinct. So that means that they're essentially the same. So this p-value is 2.2 times 10 to the negative fifth power. So that's well below 0.05. So since it's well below 0.05, we find that our histogram is not normal. And that, I know before doing this, I definitely thought that it would be normal, but that disproved my hypothesis. However, that might be due to outliers, and we can take a look at that in the next part of this video. After seeing that the histogram for the change in closing price in GE stock over the last year does not follow a normal distribution, we can check if outlier data points cause the lack of normality. With stock data, outliers can arise for several reasons, and they're often quite common. For example, if GE makes an announcement, the stock price can fluctuate dramatically. So if they announce a new product one day, then the stock price might go up. In order to account for outlier data points, we first need to create another data frame which stores all of the data from our initial stocks data frame. So that stored everything in the CSV plus the delta closing column that we created. So as you can see at the top, I imported matplotlib and pandas, and I also did the %sign matplotlib inline, so that prints figures inline. Then I created this new data frame called filtered_data, which is essentially just stocks_data with one change. So what I did was I sorted the values. This function, sort_values, lets you do that. And the parameters are the column you want to sort by, and then whether you want the values to be ascending or descending. So I wanted the values to be descending. So I set ascending to false. If you want them to be ascending, then you just set ascending to true. So then I printed out filtered data. Pandas lets you print out a data frame without print syntax. So that's a really helpful tool. And then you can see that the rows are printed out in order. So in order in terms of the change in closing price. So here's the largest change in closing price, and then there's still the empty cell down here, but here's the smallest change in closing price. So what I did then was I wanted to remove the top 10 points and the bottom 10 points so that I could have a data set which didn't have any extreme data points, any outliers. So what I did was I found the 10th highest data point, which is 0.6, and I found the 10th largest decrease, which was negative 0.43. And then I used less than or greater than signs to say that I just wanted the data in between, with closing prices in between those two bounds. And so to filter the data, I use this .loc function, which let me just say that I wanted this column, so stocks underscore data, then within that data frame, delta closing, less than 0.6. So I wanted everything that's greater than 0.6, I want removed. And then I did the same for anything. So I just said that I wanted data points that were greater in change than negative 0.43. So then I could print out filtered underscore data, which is my data frame. And as you can see, all of the top data points and all of the largest decreases are gone from the data frame. And then what I did in this line of code was I basically just removed all the columns other than delta closing. So I did this earlier in the video as well. And so that's these 6 columns. I kept the index. And then I used the same syntax as before to plot both a histogram of my data and to plot a normal probability density function. So you can see I used the same syntax here. I just changed the color. I think before it was red. And then obviously I had to change the names from change underscore closing. This line of code is different, but this is an optional line of code. The code will run without this line, so you don't need to worry too much about that. Once I printed it out, I saw here that this here looks like the normal probability density function fits the histogram much better. And so that made me think that the data without outliers, the histogram without outliers, might actually be normal. One note, up here I imported something called mlab. You don't need to worry about that. I didn't use it in here. And so then I can just run the statistical test to see whether the histogram is actually a normal distribution. And so as you remember, I import scipy.stats and stats.normal test with filtered underscore closing, so the data frame as the parameter. So then I printed out the results of that test, and the p-value is about 0.88. And so if you remember from earlier, a p-value over 0.05 denotes that two sets of data are not statistically distinct. So that means that we can say now, statistically, that the histogram and normal distribution are essentially the same. So we can show that without outliers, the histogram does approximate a normal distribution. So in this video, we gathered data as a CSV and used pandas to manipulate it. We used matplotlib to create a histogram and a normal probability density function. We used statistical tests to judge normality, and we looked at the effect of outliers. So if anything in there didn't make sense, I would strongly encourage you to go back to the videos linked in annotations. They're really helpful in giving you background knowledge. And thanks for watching.